We're going to measure the acceleration due to gravity by using this here. This is a data logger, and it's connected to two light gates. This light gate is connected to channel A. This light gate is connected to channel B. You'll see that when I interrupt the light beam, a red light comes on here, indicating that a signal is being sent down this wire into the data logger. And the same is true for the light gate that's connected to port B. Now what we're going to do is we're going to measure how long it takes for something to fall with these arranged like this. So how long it takes to fall through the first one to the second one, that distance there. So the way we set this up, we go into time and motion, press the green arrow. We want time, press the green arrow. From A to B, press the green arrow, and there we go. So it'll start the stopwatch, or start the timer when A is broken, and stop it when B is broken. Which one's A? Oh, that one's A, that one's B, there we go. So when A gets broken, it starts. When B gets broken, it stops. At the bottom, we have the mean time. We're not going to use that. That's because it records the data. We're not going to use that. We're just going to use the top one. And each time we break A, then, which one's A? Break A, then break B. It tells us the time between breaking them to 1, 2, 3, 4, 5 decimal places. Wow, that's huge resolution on that. Good. Now, the way we've got this set up, we have the ruler clamped in place so it cannot move. We've got light gate B at the bottom, light gate A at the top. And we're going to drop an object down there through light gate A and through light gate B. Hopefully this bit won't get in the way. Now what we'll do is we'll measure the distance between light gate A and light gate B, and that will be the distance as our independent variable. And then I will move the bottom one up, reducing that distance in steps. Now you can see that I have tried to line that up with the 50 centimetre mark on the ruler, and light gate B is currently on the 10 centimetre mark. So that's currently 40 centimetres between A and B. Well, to the nearest couple of millimetres, this is as closely as I can measure it. If I want to check for verticality, I can take this plumb line, so I've got a plumb bomb on the end of a string, so I can lay that down like this, and I can see whether or not the ruler is in line with the vertical. Now really I should clamp the top of this in place while I'm doing this, because otherwise it swings around. But I'm only quickly getting results, so I'm not particularly bothered if it's perfect or not. I mean, that looks pretty much vertical by eye, so I'll leave it like that. Oh, the camera seems to have slipped down. Whoop. That's going to keep on slipping. Now, we do have a few choices of things we can drop. I've seen this done where ball bearings have been released from the top using an electromagnet to get a clean release, and that's fine, but there's a lot of faff there and you don't get a lot of benefit for it. And what I found actually gives you pretty good results pretty quickly is just to drop a piece of card like this. But you don't want the card to tumble as it falls, so just a little bit of blue tack to act as ballast. That's physics putty, as we like to call it. We're going to just pop some ballast on here at the bottom, just because it will try to make sure that it doesn't tumble as it falls. Just like that. So when I let go, it should drop vertically downwards. And we've got a clean edge there, as clean as we can get it. So let's just do a couple of preliminary drops to make sure that it does fall between the light gates and that I can get a time. Whoops. Stop it for a second, hit the clamp stand in the middle. That worked. Hit the clamp stand in the middle again. That worked, but I do think it hit the clamp stand in the middle. That worked. That worked. That works, yeah. So as long as I drop it far enough away from the ruler, that's fine. But that raises an interesting problem, because I need to make sure it passes the first light gate at the same speed each time, which means I need to drop it from exactly the same height. I need a reliable fiducial marker from which to drop this. So let's go get our trusted splints. Yes, when physics putty doesn't work, we use masking tape, the greatest of all tapes, just narrowly beating duct tape. So there we have our fiducial marker, and I'll drop it so that the top of the card is level with that fiducial marker, and that way the bottom of the card is a little bit further out like that. So it's just the tip of the fiducial markers on that corner. I also need to make sure that I'm holding it so that it hangs down with the bottom horizontally, because that would be no good, and that would be no good. So I need to do some measurements and draw some pictures on this. I don't know why I'm going to all this effort, because the results will be rubbish anyway. Oops. Pen. Right, so the centre of mass is somewhere above there. Let's go get a set square. Let's line it up with the bottom, through there. I mean, when I put the blue tack in, it's not going to be exactly the right place anyway, but hey-ho. If I hold it from there, that should be pretty much vertical. If I hold it from there. Right. Right, let's just do a couple more preliminary drops just to make sure I've got that all right. So from that corner, drop it straight down. Nice. From that corner, drop it straight down. From that corner, drop it straight down. There we go. So just a little bit of care and we're going to get some results that we can use. So here we go. We're going to measure G by free fall. The first thing I'm going to do, though, is think about the uncertainties in my measurements. So I am going to write down the resolution of my instruments. Resolutions, if I can spell that correctly. I'm going to be using a ruler with a resolution of 1 millimeter. Now, actually, I'm not convinced that's quite right, because where I have the light gates lined up, let me just turn this camera around. Here, I'm not convinced I can say within 1 millimeter that that is correct. I think that that's actually going to have a greater uncertainty than that, at least 2 millimeters here and 2 millimeters at the bottom. So I'm going to say that the uncertainty in my measurements of S are actually, let's say, 4 millimeters. That's quite a liberal estimate. So I'll add that later. Actually, I'll add that here. So I'm going to put uncertainty equals 0.004 meters. That's what I'm going to say, my uncertainty in measuring S. So uncertainty S. The other instrument I'm using is the data logger. I'm just going to call that a timer here for simplicity. 0.00001 second. Now the uncertainty for that I'm going to figure out by having a range of results. So in my table I'm going to have S in centimeters. Might as well, sensible unit to use. And I'm going to measure T1 in seconds, T2 in seconds, T3 in seconds. I'm only going to do it 3 times. I could do it more than that. I could do it 7 times. That's getting excessive. And T average in seconds. And let's just start from that, and I can figure out my uncertainty in T as well. Right, let's get some measurements. 40.0 centimeters, because I have to match the resolution. Now let's get some timings. Right, let's turn this around. Move this further away. That'll do. Let's start dropping a piece of card. Ooh, the excitement. That's the first result. 0.18034. Next result. Away a bit so I don't smack it one. A little bit smaller. 0.17867. And the third result. little bit higher again, 0.18040. So, there's my first result. I'll do the calculations later. Now what I do is move the bottom light gate. And I'm going to move it 5 centimetres. So we'll do 35 centimetres next. So we're 5 centimetres up. Tiny bit higher. Just a tiny bit higher. Tiny bit lower. That's about as good as I'm going to be able to get. Preliminary check to make sure it goes through them. Try that again. Yeah, that goes through them. Good. We're ready to do our measurements for this one. Here we go. 35.0, as close as I can get it. Let's record some times. 0.16412, that's definitely lower. And again. 0.16402, so close. These timings are great. 0.16358. There we go. So my results currently look like that. Right, now let's do the rest of it so you don't have to watch. There we go. Now I wanted to keep going and get 7 data sets, 7 data points. I've actually got 6 data points. And I can't get more than that because this clamp stand's now got in the way and I can't move this up another 5 centimetres. Remember, I'm moving the bottom one, not the top one, so that the card is travelling the same initial velocity here. And I can then only measure the difference in time between these two. So I have all the results, now I've got to process them. Now when you have as many results as this, it does make sense to use a spreadsheet to chug through them, and even to produce your graphs and do the analyses. And competency 5, includes using the right tools, such as ICT, and this would be the example. I'm not going to do that because if you can do it on paper, you can do it on the spreadsheets. So let's do it on paper to make sure you know what you're doing. And so I'm going to use a calculator. How am I going to calculate the mean t? I'm just going to add the 3 t's together and divide by 3. And how am I going to calculate the absolute uncertainty in t? It's going to be the biggest one, subtract the smallest one, divided by 2. Off I go. And there we have it. There's all the calculations. Now you'll notice that these are all 5 significant figures, and yet I'm given these calculations to an additional significant figure, the 6th significant figure. Really, there should only need to be 5, but I'm doing 6 so that I have the extra digit to protect against round-off errors. With the uncertainty, I decided to present those to 5 decimal places. Why is that? Because that's 2 significant figures, that's 2, that's 2, that's 2, that's 2. We only give our uncertainties to 2 significant figures at A level anyway. This is the interesting one because it's come out to 3 significant figures matching the decimal places. But that to me looks fairly sensible, so I'm going to go with that. Now, the calculation we're going to do, we're using S equals UT plus half AT squared. We're going to calculate A, and that will be g, the acceleration due to gravity. Now, the problem is, this isn't in the form y equals mx plus c. There's a variable, that's our independent variable, but we also have our dependent variable appearing twice. And none of these terms is a pure constant. So if I divide through by t, I end up with s over t is equal to u plus half a t. Now, a is a constant and u is a constant. S over t is a variable. It contains the independent variable there, and t by itself is a variable. So this is in the form y equals mx plus c. In fact, I could write it in the form y equals mx plus c. S over t is equal to half a t plus u. And so if I write it like that, if I plot this on the y-axis and I plot this on the x-axis, not a problem, that is going to be the gradient and that is going to be the intercept. Okay? Well, that means I need to calculate S over T. I've got S, I've got T, better get calculating. Thanks to some nimble fingers and the calculator, there we have it. Blah, 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 blah. They're the data that I'm going to plot. Now, I'm going to want to include error bars in this, which means I'm going to have to calculate the uncertainty in S over T and the uncertainty in T. Well, the uncertainty in T will be easy enough because it's there already. But the uncertainty in S over T, because these quantities, this is divided by that. Let's put a bracket around that to make it a bit clearer. Because S is divided by T, that means that I'm going to add the percentage uncertainty in S to the percentage uncertainty in T. Well, the percentage uncertainty in T, I can add that as a column here. The percentage uncertainty in S, I can add that as a column there. Now you can see why it's worthwhile leaving space, if you can, on the right of a table so you can add more if you need to. So there we've got our percentage uncertainties. That was just calculated by using that uncertainty divided by that, careful of the units, and I've presented them all as percentages. And I've done that way rather than putting percentage up here in the header, because percent isn't really a unit. So they're just numbers. Right, okay, now I can add that percentage to that percentage to get the percentage uncertainty in this, then multiply that percentage uncertainty by that value to get the absolute uncertainty in that. And that's what I need to calculate. So let's add those columns. Okay, now I could have shown all those calculations, or at least one example of me doing those calculations, perhaps here, so that whoever's looking at this later knows the methodology I've used. But I've explained it on the camera, so I'm not going to bother writing it. There we go. So I'm going to plot that on the y-axis, plus or minus that on the x-axis, plus or minus that. And I might as well use this convenient graph paper that's on the left here. And there we go. I should have used a pencil because that's 1.9, not 2.9, but never mind. I've tried to choose a scale where on the x-axis it goes from about 0.08 to about 0.18, and that should occupy more than half the paper. I think it just does. That's just an okay scale, just. Vertically, we're going to go from about 1.7 up to about 2.3, 2.2, something like that. And that's plenty big enough on the vertical direction. So let's get the points plotted. Now, a bit of a pro tip when plotting is I just write down how much each small square represents. That just helps me when I'm counting it out, so I don't have to keep trying to figure it out. There's my results. They spread far enough in the x direction and far enough in the y direction. Do my line of best fit, but before I do that, I'm going to draw all my error bars. So I need to extend these in the horizontal and the vertical direction by these amounts. Now, if you look down the x direction one, every small square is 0.02. And none of these round to 0.02. That's 0.01, which is half a small square. None of these round to 0.02. That one's 0.01. So there's a tiny horizontal error there and a tiny horizontal error there, but they're too small to really be bothered plotting with. They're less than a small square on my grid. So I'm not going to bother plotting the error bars for the x-axis for that reason. Let's look at the y-axis. Well, now there are some errors worth plotting. That's about 7 small squares. So 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. That's about 7 small squares either side right there, and I'll do the rest of them. So there are all our error bars drawn, and this was really helpful in figuring out how long the error bars had to be. You can see how big some of these are. Look, 0.06, and there are 0.005 small squares, meters per second per small squared. So anyway, now we can draw a line of best fit. And it means to pass in between all of these error bars and as close to the points as possible. So I think about there-ish. I've committed to it, I draw the line. It might not be the best line of best fit, but it's what I think is pretty close. Actually, most of these points are above it. There's only a couple that are below, so it might not be the best line of best fit. Now let's draw the worst line of best fit. So it has to pass through all the error bars just. So that is the worst line of best fit right there. And I'm going to label it worst acceptable line of best fit. and above that, line of best fit. Okay, now what we can do is calculate the gradients of these, because that's going to be used in our calculation of A. And there we go. I like to write the coordinates as close to the spots as I can, so you can see which coordinate corresponds to which spot. You can even draw little arrows to label them, if that helps, but I wouldn't do too many arrows, because otherwise it will get confusing. But there we go. So now we're going to do our gradient calculations using those points. Notice that the points aren't where the x's are. They're along the line and where the grid lines are pretty close to those lines to reduce the uncertainty in our gradients. So there's my gradient calculated, and I know that the gradient is half A, so that would give me an A, which is equal to 2 times that gradient, which would be equal to, let's just do 2 times that answer, 10.43 meters per square second. Not terrible, not great. It should be about 10.43. Now let's check the uncertainty in that. Well, the worst acceptable line of best fit has a gradient of that. And if I subtract that from that, that will give me the absolute uncertainty in the gradient, which is, let's just write this down, 5.21 subtract 4.02, so that is 1.19 meters per square second, right? That's the absolute uncertainty. So the percentage uncertainty in the gradient, which will be the percentage uncertainty in G, that's a curly E there, an epsilon, that will be the same percentage uncertainty. It's going to be that divided by 5.21, which comes out at about 23%. So I have 23% uncertainty on that, which is equal to 10.43 equals, I'm using my calculator, wow. So the absolute uncertainty in G is actually let's say 2.4 meters per square second. So now when I write down what my value of G is, and I might as well do it down here, I can say that measured G is actually equal to 10. Let's match the number of decimal places, 10.4 plus or minus 2.4 meters per square second. Hey, that's pretty good. Shall we look up what it's supposed to be? Oh. There we go. So there's our use of the revision guide according to 𝗟𝗶H et al. We've got a date when it was published, the publisher, the title of it. So that's a good enough reference for the accepted value. We've restated the accepted value with the measured value. You can see clearly it's within tolerance, but you could add a sentence to just say that, and that's a perfectly good conclusion with evidence that you're looking up what the answer should be. Everything's clearly laid out. I managed to do it in just 2 pages, because mainly I didn't want to have just a little bit at the top of that page and nothing else, so I crammed it in. So it doesn't look very nice, but it's all there, so let's not overwork it. And there it is, measuring acceleration due to gravity using a free fall method in 2 pages, and it took about an hour to do from start to finish, including all the calculations.